Okay, so today what we are going to learn about is absorption, right? So you have learned before on you have learned about humidification before, right? So what is humidification? I mean, what it's used for? The process, what is the process of humidification? Who can tell me that first before we go into absorption? Because this is actually in the same chapter in your Jean Copley's book. It's in the same chapter, means the principle of operation is quite the same. So for humidification, what is the process about? Who can tell me? I will choose one person to answer the question. Oh, someone answered in the chat box. So let me see in the chat box. Where's my chat box? Okay, Amzad say is to increase the water vapor in the gas phase. Increase the water vapor. Yeah, something like that. Okay. You have a gas or air that is less humid, and you want to increase the moisture in your gas or in your air. So you will have to evaporate the water to be in the vapor phase. All right. So all this depends on the temperature of the dry air or the gas. Not gas in this case. For humidification, it's specifically for air. Okay, it's specifically for air, not for other gases. So for humidification, it's specifically for air. So you want to increase the humidity of the air. So you start with a less humidity. You want to increase the humidity, and thus when you increase the humidity, you will reduce the temperature of the water. Okay, so from that principle, you can use you can apply the principle in a cooling tower in the processing plant, so that you can like change the water in liquid phase into vapor phase, which is called evaporation process. And from the evaporation process, you get to cool down the temperature of the water that comes into the cooling tower. And when it goes out of the cooling tower, the temperature is going to be lower. So that's humidification. So remember, for humidification, it's specifically for air, not just for any gases. So today what we are going to learn, we are going to learn about absorption. And for absorption, it's not necessarily will be air only. Okay, it can be involving other types of gases or other components uh, uh, apart from the air only. Okay, so what is absorption? If you see, can you see my slides?
Yes, Doctor.
Okay, all right. So if you see here on the left, okay, this is you can put down my pointer. Where's my pointer? Okay, if you look here on the left, okay, this is how an absorption column, or two absorption columns in this case, in the processing plant. So what is it that it does actually? Okay, let me click. Oops. Okay, so in absorption, it's actually involving a mass transfer process. So you've learned transport processes before in your I think it was in the last semester you learned transport processes, or the semester before? When did you take your transport processes? In your fourth semester or in the third last semester? Okay. So you learn how to calculate flux, you learn on heat transfer as well. But in absorption, the process is actually a mass transfer. It's a mass transfer process. So okay, you listen to me. What the definition is. you have a mixture of gas. You have a mixture of two or more gases. Okay, you want to separate these gases. Okay, maybe you want to separate one gas from the mixture of three gases. But in this first part, what you are going to learn is just a mixture of two gases, binary system. So if you have a mixture of two gases, you want to be able to purify, let's say A, okay, solute A or gas A in the mixture. So you have to use a solvent to take out A from the mixture. All right, so that's the process of absorption. Absorption column or absorption unit operation is when you have a mixture of gases, but you can purify one component and you can take it out. You can extract, not extract, you can separate one component to by using a solvent. So that is absorption. So if you see the definition here, it's a process of separating a solute A. Solute A can be gas A, or several solutes from a gas phase by contacting the gas with a liquid phase. So if you have a mixture of two gases or two components, you can actually take out solute A from if it's a mixture of two components A and B, you can take out solute A or component A from the mixture by using a liquid or a solvent. Okay, or you can have several solutes, but you can also take out more than one component from the mixture of gases or solutes or components into the liquid phase, which depends on the solubility of the component into the liquid phase or into the solvent. Okay, so this very much depends on the solubility of the component that you want to separate on or in the solvent that you're going to use. Okay. All right, so for example, okay, this is just some example in processing plants or in our daily life. You want to absorb ammonia from air. Okay, you have a mixture of ammonia and air, A and B, using liquid water because ammonia is soluble in the water. Okay, or you want to separate acetone from air also using liquid water. These are all possible because the solute that you want to remove or absorb are all soluble in liquid water as a solvent. If it's not soluble, then you have to use other solvents. Okay, you have to choose another solvent where the solute or the component that you want to separate will be soluble in. Okay, and then for your content in this course, you will have to make this assumption where the liquid phase is actually immiscible in the gas phase. So you have A plus B, A being the solute that you want to, or the component you want to separate. B is the carrier of the component you want to separate. C is your solvent. Okay, let's see. So B being the carrier and C being the solvent or the liquid. The C or the liquid will not be mixable in B. All right, so that's an assumption that you will make. So the only thing that's moving is the component you want to separate. In this case, or in that example, the component is component A. So component A is the only component that is moving from a phase to another, or from a carrier to another carrier. Okay? All right, so that is absorption. So in the chemical plant or in a processing plant, you will also have a process called stripping or desorption. It's actually the opposite of absorption. If in absorption you have a mixture of gases, A and B, or A plus B plus C plus D, or A plus B only. But in stripping, you have a mixture of liquids. So you have liquid A and B. You will use a gas to absorb the liquid A. Okay, so stripping is the other way around. For absorption, you want to, the component that you want to separate is in the gas phase. For stripping, the component that you want to separate or absorb is in the liquid phase. So it's actually the opposite. So the solute is removed from a liquid by contacting it with a gas. So it's the opposite of absorption. Okay, so before we go into the calculation or the designing of an absorption column, so first you will have to look at the gas liquid equilibrium principle, where we will be looking at Henry's laws. Okay, so in Henry's law, okay, I'll just press enter so that we will have everything on. Okay, so in Henry's law, this is the equation that is invented, which is PA equals to HXA, or YA equals to H prime XA. So PA is partial pressure of component A. So if you have a mixture of two gases, okay, A and B, so you will have partial pressure of A as well as partial pressure of B. So I'd like to know who here can tell me what is partial pressure of A. What is partial pressure of A? Can anyone tell me, or I will have to call out some names? Anyone can tell me what is partial pressure of A? So let me choose someone. Ki Nadra, can you tell me what is partial pressure? How to calculate partial pressure? You have learned this in your ITE, I think. ITE, you learned this in the few subjects you've taken before. So what actually is partial pressure? How do you calculate partial pressure of a gas from a mixture of gases? Okay, are you there?
Yes, Doctor.
Do you know what a partial pressure is?
Yeah.
No, you don't remember what partial pressure is?
Not
Okay,
really.
not really. So who can help Key? Anyone can help Key? Can I have Lavintran? Lavintran, do you know what a partial pressure is? Are you there, Lavin?
Yes, doctor.
Can you tell me what partial pressure is?
Partial pressure is like it's a mixture of gases.
How do you calculate partial pressure?
Yeah.
This is very basic for chemical engineers. You have to be able to calculate the partial pressure from a mixture of gases. So how do you calculate? Do you remember? From the courses you have taken before, I think one of the subjects have covered this. No? No, Lavin? So if you cannot tell me, then I'm gonna have to go to Mark Naim Hairi. Mark Naim Hairi, what's your full name actually? I'm just using your WebEx name.
Sorry. Naim.
Naim. Okay, Naim. What is it? Partial pressure. Do you know what is?
Mole fraction times total pressure.
Yes, mole fraction of the component that you want to know the partial pressure times the
Total
total
pressure.
pressure. Yes. So that's actually what it is. Okay, thank you, Naim. Glad that you remember, or you can just Google actually. This is an online class. You have to be clever, you know. Okay, so let me show you the principle. I think you have learned this before. It's either that you I think what you are facing now is like you learn something but it's not really sticking in your head what it is actually. So today I'm gonna try to make you remember what partial pressure is. Okay, so in a container, let's say in a container, there is a mixture of, let's say, A and gas B. Okay, so you will have mole of A and mole of B, and you will have pressure equals to, you have pressure, this is total pressure, P is total pressure. Okay, so for this mixture, okay, for this mixture, if you want to know partial pressure of A only, you will have to take YA, sorry. So for the capital P, it's a total pressure. If you use small p, okay, this is actually partial pressure of A. So you will take the number of mole of A multiplied by the total pressure, which is capital P. Okay, so if you take PA plus PB, it's actually equal to the total pressure. Right, this is the fundamental equation. So if you have a mixture of gas A and gas B, you can calculate the partial pressure of A by knowing the mole fraction or the number of moles, not the mole fraction. Yes, that's the same. Mole fraction of A times the total pressure. If you have PA and you have the total pressure, you can calculate the PB as well. All right, so I hope you remember this. You will remember this for quite a while. Okay, so that is actually what partial pressure is. Okay, so for Henry's law, what it's saying is that, okay, partial pressure of A is equals to X, which is the Henry's law constant, times XA. So if the fundamental is the fundamental equation is relating the partial pressure to the total pressure, right? Now, the Henry's law is relating the partial pressure to X. X is the mole fraction of liquid A. Liquid A. All right? So, this is YA is the mole fraction of A in gas phase. XA is the mole fraction of A in liquid phase. So this is when we use the Henry's law constant to relate partial pressure to the liquid mole fraction or the mole fraction of A in the liquid phase. Because from what we know from the fundamental equation, we can only relate it with the mole fraction of component A in gas phase, okay, in the gas. But now we have or we need to relate the partial pressure to XA as well. All right, so another equation that you need to know is the relationship between XA and YA. So if you use Henry's law constant H, okay, not H prime, you will get to relate PA and XA. If you use the Henry's law constant of H prime, you will get to relate YA and XA. All right, so I hope you will be able to apply these equations when you need it. I mean, if you are given with a relationship or with a condition or question where you need certain mole fraction that you do not know, then you can think of Henry's law to be used as well to relate or to have, if you only have XA, now you want to find YA. So you can use this equation. If you have XA, you want to find YA, then you can use the H prime. Okay, so I will show you how the application of these equations in a question in a while. Okay, so this is the principle where how they derive the Henry's law constant in a mixture. So for a certain mixture, in this case it's sulfur dioxide, which is SO2, in gas phase, and then this is sulfur dioxide in liquid phase, as a relationship. Then they will have to take the gradient to be the this equation. Okay, and then you can get the Henry's law constant. So the scientists before us, they have done all the correlation for us, and they have derived the Henry's law constant for certain mixtures. Okay, so we can today we can use those constant. If you see in appendix A.318 in your textbook, I'll show you how the appendix looks like in a while in an example of question. Okay, so actually for what they derive is the Henry's law constant tabulated in appendix A.318. But for H prime, it's actually you take that H, you'll divide that with the total pressure. So if you have H, you can derive H prime if you have the total pressure of the mixture. Okay, so this is an introduction of a principle or Henry's law that sometimes you have to use in an absorption question or situation or condition or process. Okay, so let's look at the next slides. I think the next slide is to show you how this Henry's law can be applicable. Okay, so it's usually applicable in this case. Yes, Lavin, do you want to ask question?
No, Doctor.
No, okay. If you have question, just let me know. Okay, I'm just going to go on if nobody's asking anything. Okay, so the Henry's law can be used as in this application where you see a single stage equilibrium contact. So in humidification, you have been introduced to a few terms, so symbols like L1, L2, G1, G2, HY is where is the enthalpy, H is the humidity. Right, for a single stage equilibrium contact for absorption, you have to learn another set of terms and symbols. Okay, so for an absorption process, this is how the schematic diagram would look like. Okay, so in this case, this is the absorption unit. All right, and V will stand for vapor, not for vapor, it's gas actually. V is gas, L is liquid. Okay, so you have the mixture for absorption, the mixture is in the liquid or in gas phase. Have you been listening to me? So for absorption, where is your mixture?
Gas.
Gas, right? So you have a mixture of gases. So you have this mixture of gases coming in, and you put this solvent in a countercurrent mode. It can be in co-current, but usually it's done in countercurrent. Okay, so the solvent will come in there, and then you will have the mixture of gases A and B here, let's say. All right, so because A is soluble in the solvent and B is not soluble, That's why you choose this solvent, because only A can be soluble in it. If both can be soluble in it, you cannot choose that particular solvent. Okay, so you have this solvent coming in, you have the mixture of gases coming in V2. Okay, then when they are in contact, okay, in this single stage, A will be transferred into L0. Okay, so when it's transferred into L0, it's gonna go out of the single stage as V1. And it's gonna go out as L1, not V1. It's gonna go out of the process or the column or the stage as L1. So now this is C, let's say, and this is A plus B, right? And then when A is transferred into C, then it's going to be into L1. Here you will have A plus C. And what's left over here in V1?
B plus C.
What's
Sorry.
going to be left in V1 here?
B plus
B plus?
A.
B plus A. Yes. B plus a little bit of A if the absorption is not total. Okay? So you will have B mostly and a leftover of A that is not transferred into the C. Okay, so this will depend on the statement or condition you have put for your single stage. Let's say your statement is to remove 90% of A. All right, so you have here A plus B. Okay, so you want to, let's say you want to remove 90%. Remove 90% of A from the initial mixture. So the 10% of A is going to be here, the leftover. And the 90% of A is going to be there, 90%. Not 90% of the flow rate, but 90% of the initial A that comes in. Okay, so that is when your mass balance is going to be handy for you. You have to use your mass balance knowledge for you to be able to know all the mole fraction of the components in this process. So that's why in your program, in your curriculum, you learn mass balance first, and then you learn transport processes, and then only you will take separation processes. So it's in sequence so that you will use the knowledge from one course or subject, you will use it in the next. Okay, so that's why the prerequisite for separation is transport processes, so that you will have all the fundamentals already to know how to do separation processes. Okay, so if you see here, liquid and gas phases are brought into contact and separated, okay, in the single stage equilibrium. And if they are in contact for a long enough time, it will achieve equilibrium. Okay, so in the gas phase, you have solute A and inert gas B. Why do you call inert gas B? Because B from V2 is not going to go into the L. It will stay in the V stream. Okay, that's why it's inert. And for the liquid phase, you have solute A that is transferred from here, okay, into the inert liquid solvent C, because C here will not be transferred into V. It's going to stay in L, okay, in the whole operation, okay. Then now you will look at the total. Who can give me, you should have your notes, your lecture notes with you, right? So from your mass balance knowledge, from your mass balance course, you will be able to do the total material balance where you will take input plus input equals to output plus output. So for the flow rate, okay, this is for total balance. You'll take the flow rate of L naught, okay, because it's the input plus V2 equals to L1 plus V1, okay. And then you will do component balance. Okay, from mass balance, you learn this, right? You will first do the total balance and then you will do the component balance. So the components that we are interested in is component A, because that's the only component that's moving. Because components B and C are all inert. They don't move, it stays in the stream. Okay, so for the component balance, which is balance on A, you will take the respective mole fraction in each stream. So if you see here the terms and symbols for L naught, you will call the component A in L naught as X. Okay, X, A is the component, naught is the stream, L naught. So the flow rate times the mole fraction will be the first expression there for the input. Sorry. Sorry, guys. Okay, so then you will look at V2 next. Okay, and then what is the mole fraction in V2? Sorry. So the mole fraction of A in V2, minus V2 here is YA2. So you times the YA2. Now you look at the outputs, which is L1 and V1. For L1, the component mole fraction of A is XA1. And for V1, the mole fraction of A is YA1. Okay, so this is actually your material balance and component balance. Okay, all right, so now I want to introduce you to something new. This is what you learned in your mass balance. Okay, this is what you learned in mass balance before. Now this is unique to separation processes. You will only see this here, I think, for the first time throughout your program. Okay, so this is a new equation for you to know where it comes from. Sorry, saya ni pagi-pagi memang macam ni lah. Okay. Right, so now from this schematic, you see L1, you see L0 as the liquid streams, and you see V2 and V1 as the gas streams. Now already I have covered this where who are the inerts? You have two inerts. You have the inert gas and you have the inert solvent. Now, because B and C are not moving anywhere, they will stay in the stream, right? So we want to call the flow rate of the inerts in the liquid and the inert in the gas phase a term. We want to give them a symbol. So the flow rate of inert C, which is a liquid, is called L prime. Okay, the flow rate of inert B, which is the gas, is called V prime. Okay, so now I want to show you how you derive this equation. All right, so let's say for this stream, there are A plus B in that stream. So how do we get the L prime? Okay, how do we get the L prime? We will use the equation of mole fraction. Okay. Okay. So mole fraction of A, YA2 is equal to what? Who can tell me what YA2 is?
YA plus YB
Y?
plus YB.
YA plus YB. YA plus YB. Okay. Now, I think I'll change my question. You have some idea here. but YA plus YB is equal to 1, right? Sorry. So if you, who is it just now? Is it, I didn't see who was speaking. I said YA plus YB just now. Ki ke? Tak dengar. Elma. Okay. So Elma said YA plus YB, but YA plus YB is actually equals to 1 because there's only A and B here. If you take mole fraction of A plus mole fraction of B, it's actually equal to 1. So to get YB, okay, is equal to 1 minus YA, 2, isn't it? Right. So to get YB2, let's say YB2 over here, it's 1 minus 1A2. So in terms of the mole fraction, okay, in terms of the mole fraction, in terms of the flow rate, okay, you will have, if L prime is the flow rate of A, flow rate of B. All right. So L is actually, sorry, not L lah. Kita will talk on Y kan. So V prime lah. Okay. V prime is only B. So now for V is actually V prime plus V of A, isn't it? V2. Right? So how do you get V2? It's actually mole fraction of A times V. 2 is actually A, right? Mole fraction of B times V2 is equals to B. In terms of flow rate, right? Sekejap. Jagi air. Ada something sekejap. I'll be back. Give me 5 minutes. Sekejap. Okay, sorry. Okay, now our goal is to change L from the original equation here. You see the original equation is L naught, right? Now you want to change L naught to L prime. So let me just erase all of this so that you're not confused. Okay, our goal is actually to change, okay, we want to change L naught into L prime. Why do we want to do this? Because there's actually how many unknowns here? 1, 2, 3, 4, 5, 6, 7, 8. So in order for us to do the simultaneous equation to solve them, you need to reduce the unknowns. So that's why we need to derive this equation. So this equation is actually reducing the unknowns from 8 to how many? 1, 2, 3, 4, 5, 6. Okay, because now you changed it into L naught and V naught. So from 8 it becomes 6. Okay, so let's see how you change from L to L prime. Okay, so for a stream, let's say take stream L naught. So let's say we take this expression. Okay, so for L naught, okay, if you have A as XA naught, and B as X B naught. Okay, who can tell me what is the flow rate of B, which is L prime? How to get the flow rate of B? The flow rate of A is X A naught times L naught. Here, right? So what is the flow rate of B? Given that X A naught plus X B naught equals to 1. So if you know X A naught plus X B naught equals to 1, and you are giving the mole fraction of B as X B naught, what is the flow rate of B? So remember, L prime is, sorry, not B, C. I know, don't get confused. For the solvent, it's C. So what is actually, so this should be C lah, C naught. Okay, so what is actually the flow rate of C? Here. Can anyone tell me? If for A, okay, flow rate of A, for A is actually X A naught times L naught. Now for B, what is it? Flow rate. The number of moles per time. Who can tell me that? If you have here X A naught plus X C naught equals to 1. So who, sorry, not B, ya Allah, I'm still confused. B is for the gas. C, now C, we are talking about L naught. So if for A, flow rate of A is X A naught times L naught, for C, what is it? When you know this, X A naught plus X C naught equals to 1. So what should be for C? Can anyone tell me that? Do you get this? Called mailing. Oh, who is it? Who wants to answer just now?
Doctor, it's me.
Lee. Yes, Lee. Is it Lee?
It's me, Doctor. Clock mailing.
Oh, called mailing. Okay, called mailing. Mailing.
So C will be bracket 1 minus XA naught times L naught.
Oops. 1 minus XA naught times L naught. Okay, so thank you, mailing. Good. So if you have A is XA naught L naught, if you know this fact or this equation where XA naught is plus XC naught is equals to 1, then you will have 1 minus XA naught as the XC. So XC naught will be equal to 1 minus XA naught, right? So for C, the principal equation is for C is going to be the mole fraction times the total flow rate, right? So what is mole fraction of C? Mole fraction of C is 1 minus XA naught. What is the total flow rate? That is L naught. So from this equation, now C has a new name, okay? Not C. The flow rate of C has a new name, which is L prime. So that's why when you insert L naught here as this, then you will get that equation. Okay, so from this equation, which is L prime equals to 1 minus XA naught times L naught. So L naught is equals to L prime over 1 minus XA naught. Right? So from this equation, you will put all the you will insert for L naught, then you will get this equation. Do you understand this? So that's why here is L prime. It's actually, this is for the inert, the mole fraction of the inert. 1 minus XA naught is the mole fraction of the inert. So you put all this, if you see, and to make it look nice, it will put XA naught over 1 minus XA naught. For YA2 over 1 minus YA2. For XA1, it's over 1 minus XA1, and so on. Okay? So this equation actually comes from the principle of the mole fraction. Okay? Because of all the derivation that we've done, now you know. What time is it now? Okay, this shouldn't take too long actually for Henry's law, because I should go into absorption principle already. Okay, so from this governing principle, okay, relating between L prime and L naught, okay, if you know the equation for L naught, then you substitute all L naught with the L prime equation. For V2, you can also substitute that with 1 minus A2, because 1 minus A2 is going to be for B. 1 minus XA naught is for C, right? 1 minus XA1 here. XA1 here, it's for C. And 1 minus XA1, YA1 is for B again. Mole fraction of C and mole fraction of B. So we don't want to be using a lot of unknowns. So we want to use only XA1 and XA2. And usually the beginning or the starting mole fraction, you will know. So XA naught is usually known, okay? YA2 is also known because you will know what's coming in and what's coming in there. What you don't know are the outputs. Flow rate and composition, you don't know usually for this single stage. So with that known, and L prime, V prime, L prime, V prime are also known. So you are left with only two unknowns. Okay, so when you solve simultaneously with this equation 1, let's say, and then this is equation 2, you will be able to solve for XA1 and YA1. Okay, so because you usually know that, and you usually will have a number for that. So let's look at a question where we can apply this principle. Okay, so let's see. And this is example 10.31 in your textbook. I'll just go briefly because you only have about 10 minutes to cover this. All right, so for this question, a gas mixture at 1 atm pressure, absolute, containing air and carbon dioxide, is contacted in a single stage mixer continuously with pure water at 293 Kelvin. The two exit gas and liquid streams reach equilibrium. These are just the conditions. The inlet gas flow rate, this is the flow rate of your V1, okay, which is 100 kilogram mole per hour. This is total flow rate with a mole fraction of carbon dioxide of 0.2. That's only the mole fraction of your A, which is carbon dioxide. The liquid flow rate entering is 300 kilogram mole water per hour. So the liquid coming in is pure water. There is no A in it yet. Okay, so calculate the amounts and compositions. You need to know the amounts and compositions. Amounts is flow rate. Why do we call it flow rate? Because it's per hour. Okay, if it's only kilomole, no, per hour is not flow rate. So in here, it's asking you to calculate the amounts and compositions of the two outlet phases. assume that water does not vaporize to the gas phase. So that means you will not lose any water component or water into the gas phase. All right, so this is how it looks from the question. You will have 100 kilomole per hour of V2 containing 0.2 of CO2. So now your A is CO2, your B is air, and your C is water. Okay, those are your components. So in your gas flow, you have 0.2 of carbon dioxide in the total flow rate, and then you will have a solvent of 300 kilomole per hour with 0 carbon dioxide, which is pure. All right. So you want to calculate what is L1, what is XA1. You want to calculate what is V1, also YA1. So this is when you use the Henry's law. Okay. Now you start with a balance on A. This is the total balance. Okay. So you write the equation based on the inert. Okay. So now you can actually calculate what L prime and V prime from this equation that we derived just now, right? L prime is L naught times 1 minus XA naught. So you know that L naught is 300. XA naught is actually 0. So you will have your L prime as 300 kilomole per hour. For V prime, here, you take the condition for the V2. Okay, to know V prime, you take the V2 times by 1 minus YA2 because you know what YA2 is. YA2 is 0.2, which is given by the question. Okay, so in the end, you will have V prime as 80 kilomole per hour. So when you know these two, L naught and V naught, which is 380, then you will be putting them into, into this equation. Okay, insert all the known values into those equations. So 300 is the L prime, you put into L prime. 80 is the V prime, and you put into the both V prime. And you put all the known information. You know XA naught, which is this. You know YA naught, which is that. Okay, so from there, your final equation will become like this, which only contains 2 unknowns, like I said before. So you can calculate everything. Okay, now what you have as unknowns are upper. You have unknowns of XA1 and YA1. So this is when you use Henry's law, because you want to be able to relate X and Y. Okay, so you look at the Henry's law constant in the back of your book that I attached in e-learning, which is the GenCorp list. If you look at Appendix A3-18, okay, so these are some of the constants, Henry's law constants for gases in water. A lot of types of gases here. A few gases, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are listed here. So what we want to see is CO2, where this is actually to absorb carbon dioxide in H2O, in water. So what you have as the temperature, you will take that. It all depends on the temperature. Okay, if you have lower or higher temperature, you will have different constant. So in this case, the constant is 0.142. So you have to know how to use this table, because here what's listed here is H times 10 to the power of minus 4 is 0.142. So if you want the H, you will have to take 0.142 times 10 to the power of 4. Not negative 4, but 4. Because what's listed here is actually H times 10 to the power of -4. Okay, so from that Henry's law constant, you can now relate between y and x, okay, using the h prime. How to get h prime? H prime is equals to the Henry's law constant over the total pressure. You are given with the total pressure, which is 1 atm, because this Henry's law constant is given in atm unit. So for your system just now that is mentioned in the question, the pressure is 1 atm, and this is the constant you get from the Henry's law table just now, and you will finally get your h prime. Okay, so from your h prime, this is known and this is known. Now you will be able to relate y a1 to xa1 with this equation. All right, so you want to be able to solve this, right? So now, okay, you will put this equation of y a1 equals to 0.142 times 10 to the power of 4 x a1 into this equation. You substitute all those in y a1. Okay, substitute all those in equation. Substitute that into y a1. So finally, you'll be able to calculate x a1. So you see, from the Henry's law correlation, you will be able to solve that equation. So that's why the Henry's law is very handy for you to use. And when you already have xa1, then you can always go back to equation here, equation 2, okay, to this equation. Then you can always substitute the y a1 that you have, sorry, the x a1, because you already calculate x a1, right? So put your x a1 into there, then you will be able to calculate y a1, which will be 0.2. Okay, so from that, then, okay, you go back to the L prime equation that we know just now, where L prime is equals to the total flow rate times the mole fraction of the inert. How do you get the mole fraction of the inert? It's just 1 minus the mole fraction of your solute, which is your A, and then you will get your L prime. Then how to know L1? Okay, you already know what L prime is from the previous calculation, right? So L prime equals to 300. V prime is equals to 80, right? Here. So from this equation, sorry, okay. So from the value that you know here, which is L prime and V prime, right? Then you can solve for V1 and L1 from those equations. And finally, what you get is for L1 and V1, which is required by the question, where it's asking you to find the amount and the mole fraction. So the mole fraction is xa1 and ya1. And the amount is L1 and V1. Do you get this? So this is only for single stage. So what's actually happening in the processing plant, in a chemical plant, is multiple contact stages. So those are only some principle for you for one stage, which is for one stage. So in the next class, we will be looking at a process where you have more than one stage. Okay, it's a multiple contact stages, which is always the case in a chemical plant or in a processing plant. Any question before we stop for today? And then we'll continue on Sunday with this counter-current multiple context stages. Any question, boys and girls? Ada yang tak faham tak? Do you understand what I teach today? Do you understand? Ada yang tak faham tak? So now you get everything that is covered today, right? So in the future, if you are given with XA, then you will have to know how to find YA from the Henry's law constant. Okay, so sometimes it's going to be handy for you to solve an absorption question, because sometimes you're not given with all those unknowns. Yeah, they are given in unknown. So from XA, you need to be able to tell what is the YA from the Henry's law constant. All right, so I think that's all for today. You have another class. You have a class at 11 with you have classes at 11? Yes, okay. What class do you have after this? Gosh, okay. All right. So I hope you do get what I covered today, because you are going to use the content or the knowledge or equation that I've shown you today in our next classes for the core, the hardcore content of the topic, which is the counter-current multiple context stages, where your test 1 actually will cover until here, the multiple context stages. Okay, it's up to this 3 tower. Okay, so until then, until next week, so that's all. You can ask me any question. If you do have some, you can personally message me as well. All right, so I think that's all. I'll see you again next week on Sunday. Okay.
Doctor, the QR code for today attendance.